Yeah, thank you very much. So, yeah, it's our pleasure to be here, and we would like to talk about a topic that's very interesting in our minds. It's neural architecture search and how it can help you to bring AI onto embedded devices. So, green button. Oops, one back, please. I jumped ahead a bit, but I think there was already introduction. I'll write this back. Okay, that makes sense. Okay, I think there were already quite some introductions here, but yeah, my name is Dominik Loroch. I'm from Fraunhofer ITWM, so it's a mathematical institute in Kaiserslautern, working in the Department of High Performance Computing on the topics that were mentioned before. And I'm joined here today by my colleague Tilo Borchardt from Getemed.
Yeah, hello. My name is Tilo Borchardt. I'm working for Getemed, a medical devices manufacturing company, and I'm in charge of IT and cybersecurity. And green button. Huh? Now it works. And what we like to yes, okay, sorry. We would like to show in this session what the potentials and problems of embedded AI are. And we want to demonstrate this on an example of the H2 project, which is about running AI on the extreme edge via neural network, neural architecture search. And at the end, we will give you an outlook what neural architecture search technology can do for you. Our example use case is ECG telemonitoring in cardiology, especially the search for atrial fibrillation by means of small wearable devices. The detection of atrial fibrillation can be crucial in preventing complications such as stroke and heart failure. And traditional ambulatory ECG monitoring often fails to detect atrial fibrillation in a single test. That's why multiple tests and delayed treatment are often the consequences for the patient. An enhanced monitoring period can help to detect events of sporadic nature, and continuous monitoring with wearable devices over a long time can reduce the need for hospital admissions and expensive diagnostic procedures. A problem that we are facing with embedded AI is that the design process cannot not scale with the demand. The demand for embedded AI is growing, but we see that organizations, or 65% of organizations that have recently invested in AI, fail to see tangible results. The problem is that we have a lack of qualified engineers, high-skilled experts, which creates a bottleneck, and that's why the development costs are high and the development time is very long. The solution is automation. The background of the H2 project is a competition of the Federal Ministry of Education and Research about energy-efficient AI systems. The University of Kaiserslautern and Fraunhofer ITWM took part in a consortium with the idea to detect atrial fibrillation on ECG data by means of FPGA chips. The approach was to use holistic code design via hardware-aware neural architecture search, and they won the first prize and received further funding for a follow-up project, which is called H2. And this is done together with Getemed and the Charité University Hospital here in Berlin. And the goal of this project is to build a real ambulatory ECG device with embedded AI. The state of the art in ambulatory ECG monitoring can be characterized by 3 types of devices. The first one is the so-called Holter recorder, which is a device that is typically worn by the patient for 24 or 48 hours. And this is the gold standard. It produces a full disclosure ECG, but the application time is relatively short. The second one is a patient-activated event recorder, which can be used for a very long time, but it can only capture symptomatic events because the patient has to activate the recording. And the third one is also event ECG, but it's continuously recording. It can be worn by the patient for between 3 and 14 days, and it analyzes the ECG data on the device and can in this way also capture asymptomatic events. The problem is that the power consumption of the battery limits the runtime of the device. So I will hand over to Dominik.
Thank you very much. So, what we need to do, we have the improvement is twofold basically. So we need to decrease the false alarm rate, right? So we need a device that is more reliable, that patients can actually trust and that the doctors can trust. And also, as has been said, for the wearable ECGs, you want to have a high energy efficiency of the solution, so you can wear it longer time. The longer you can wear it, the more you can trust the system, the more likely it is to catch those atrial fibrillations, those heart failures, that they can be detected and reported to the doctors. Yeah, so it has two components, basically more on the algorithmic side and more on the hardware side, and the way how to approach this requires a holistic perspective on this problem. There are two vectors or two solutions that we are looking at. First, the algorithmic side, we are using deep neural networks compared to some, let's say, peak detection algorithms that were running before this on a similar device. So what is great about deep neural networks is that they have a flexible structure, right? That they can be kind of like molded towards the hardware, and that they can be configured in such a way that they are very nicely fitting onto the hardware. They can be trained to do basically any task, right? So atrial fibrillation, or if you want, they can do something like detecting tachycardia or any other heart, thing that you want to detect. And yeah, the adjusted performance is what is meant here is that you can train the neural networks on data, right? So also potentially, if you have better data, you can train better models, you can improve the performance of your device. So this is the algorithmic side. On the hardware side, we also decided to use a completely new technology compared to what was before there. So before we had a microcontroller, right? So kind of standard device, but what we are using is an FPGA. It's a device that you can electronically reconfigure to basically have like any hardware architecture that you want on it to be. So advantages of this technology is that you have configurable logic. That means that you can directly program 100% what it needs to be, what it needs to do. Can be highly parallel, similar to a GPU, that you can perform multiple instructions in parallel at the same time. Therefore, it's highly efficient, very application specific, very energy efficient. Okay, but now the question is, now we have those two great innovations, deep learning, FPGA chip, but how to bring those two things together. It's a task that's very demanding, and usually how people would go about it is that they would have two experts here, right? So one from the algorithmic side, one from the hardware side, that need to work together on this problem. And starting point could be, for example, the machine learning engineer says, okay, I have now this deep learning model, it works great on the task, can detect this atrial fibrillation, now please bring it onto this FPGA device. The device engineer then takes this model, looks at it, tries to do something, and says, hey, like this doesn't fit, it's too big, it's too slow, whatever, right? It can be oversized. And then it basically gives feedback to the machine learning engineer. This loop can continue, right? In the worst case, those two those two teams, they don't work with each other very often from two different companies. So this can take months. It can take months until we have a solution for this problem. And in the worst case, after all these iterations, we have a solution that's not even really working. And then what to do. You can say that AI doesn't work for you, right? And end it there. Say it's not a technology that we can use. So, and that's where neural architecture search comes into. It's basically an automatization of this loop. What you can see here is that this basically the design phase of the model is now automatized. And also, and this is an interesting thing, you can loop back the information that you get from the designed model that you have tested on the device back into the search, right? So you can kind of have a closed loop that was before those two persons. Now we have like just algorithms doing it. Algorithms that send the data into the real device, do measurements, feed it back into the learning algorithm, and learn how to design the perfect neural network for your application. And this is basically the solution we have been engineering in this HAFT competition, and which we are also using in the HAFT 2 follow-up project. And for the technical people here in the audience, I would like to show this slide, kind of explaining a bit more what it is about. So you can imagine we are having multiple layers of abstractions, right? Starting at the very top with the, so to say, topological level of the neural networks, going down to a hardware architecture description. So how this, how is the algorithm executed, down to the realization, the implementation of the architecture on this FPGA chip. You can see there's an information flow, basically from the top, from the topological side down to the implementation, where you do the measurements and information goes back up to the top. Right? So it's this closed loop kind of thing. On the very top, where the design cycles happen, there's like many ways how you can do neural architecture search, but what we are specifically using is evolutionary algorithms. So you can imagine basically all topologies or neural networks, they are basically just genetic encodings, so they're like individuals that we can then mutate, produce offspring, produce children. And those children are neural networks that we can then evaluate, see how well they work on the hardware, do selection, see what kind of topologies, what kind of networks worked very well, and iterate the cycle. There's a lot of know-how from our side going into this, right? So it's not as trivial maybe as I said here, because there's like some inefficiencies here. But it's a very useful approach because it allows to do black box modeling. You don't need to know what the hardware exactly is. You can just query the hardware and find out how well your candidates work on this specific platform. One word to the hardware architecture itself. So it's kind of like you can imagine some kind of template, so some kind of like hyperstructure that we can fill with different building blocks, so to say. And those building blocks are basically logical implementations of the operations that we have. And giving those two things that we have, on the one hand, this hyperarchitecture and the neural architecture search that finds out what is the best implementation, we have a fully automatic system, basically, to design neural networks on specific hardware platforms in a black box modeling fashion. So the results from what we are doing now in this project together with Getemed is, we can see on this slide here, so an overall improvement. So before we had this device that's shown here, it has, as I said, it had a microprocessor, it had a battery, so you need to open it to replace a battery, and it has rather large form factors with those, let's say ears, because of technical reasons. That makes it a bit maybe uncomfortable to wear sometimes. So what we can do, since we have a smaller device that requires less energy, is algorithmically better, we can now have a leaner form factor, right? We can build a smaller device that is that doesn't need a battery, but is rechargeable, right? So you can basically now recharge it. You don't need to open the device to replace the battery. And with this, we had basically a completely redesign of this device, right? So it's a completely new solution in a way that can be used by the users or the patients in different ways now, right? They don't need to, take it off so often, or it's like much more comfortable to wear. And so the results in numbers here we can see on the right-hand side. We could increase the operating time due to this FPGA chip, and the algorithmic side is running on it. Basically double the wearing time from 14 days to 33 days. Which means that it's much more reliable. Those hard anomalies can be caught much more reliable. The power this comes of course from the halved power consumption that was reduced from like 5 milliwatts to like 2.6 milliwatts. And on top of that, compared to the classical algorithm, we could also increase the sensitivity of the model. So basically before it was 85%, and now it's 95%. So also an improvement on the algorithmic side. So you can wear it longer, and it's also returning better results. Okay, in the last 5 minutes, I would like to give an outlook what does NAS for you, or when should you maybe think about using this kind of neural architecture search as a technology. And I would first ask a question: where are you using AI applications? Where is your AI application running? If the answer is on the cloud, then you're dealing with scalable hardware resources, right? So the best option you have here is to take an existing model or something that's kind of like solving your task, and then fine-tune it to the task that you actually have at hand. So let's say it's less about even thinking too much about the model realization of the deep neural networks, but about the scalable hardware resources. But on the edge, you have a different scenario. Here, suddenly, you cannot scale the hardware resources. You are limited. And with this, you need to think about what you're implementing on this hardware so it runs efficiently and it runs at all. So another point is how can NAS help you basically? So we have seen an example from our case, from working together with Getemed, but on a more abstract level, it can help you make much more educated decision about your designs. So when you are thinking about AI and embedded, you might think, okay, embedded GPU. This is usually something that we see very often, that people tend to this kind of solution because they say, okay, I've trained my models on GPU, I know they run there, I just use an embedded GPU for this. We can see that there are other factors that can come into play. One is the cost, right? So an embedded GPU is not cheap. It's pretty heavy and it uses up a lot of energy for an embedded device. If it would be possible to run the same model or your model on a device that's much smaller, much cheaper, much more energy efficient, then it might be just a much better use case for you. Or like much better platform to use. And this is basically, you have like a whole, it's just 2 devices here, but you have a whole bandwidth of different devices that you could consider, right? And to find out what is for your project, what's the best device, this is something that a neural architecture search can also help you with, right? You can basically find out for your problem, for your data set, what is the device that you need to choose to run your model, where does it run with the accuracy or the performance that you actually require for your problem, so you don't over-invest into solutions. Okay, to summarize the talk, so what does NAS do for you? What kind of values does it give? It reduces development time, right? So instead of having this loop of a machine learning engineer and a hardware engineer, it's kind of like in one thing, and automatizes this process so it can reduce the development time from potentially months, right? Depends always on the team and so on, to something like maybe weeks, even days, depends. The cost for hardware, this was the last example, right? So you can actually see what kind of platform you need for your devices. It saves resource and energy, what we have seen the example from Getemed, and it can even allow you to think about completely new edge AI solutions, right? You have the possibility to see if a certain AI task, let's say, can be outsourced onto the edge or into an embedded device. You can find out with this neural architecture such technology in principle. And finally, to loop back to the first slide, it is a way that that AI design becomes scalable. You don't need to do this by hand. You let the AI design AI. So thank you very much.